Hi, today I will be solving educational at first round. Let's go. So in this problem, we have some number of lamps of three different colors, and we asked if we can place them in one line such that no two adjacent lamps will be of the same color. This classical problem, and the answer is no, if and only if there is a color such that number of lamps of this color is strictly more than number of lamps of other two colors plus one. Um, it is easy to see that if this condition is fulfilled, then the answer is no, because we can divide all the lamps in a row in pairs. Maybe one last lamp will have not a pair, and in each pair, at least one lamp shouldn't be not the color that is big one, and the number of pairs is smaller than the number of lamps of big color, so there is no solution. And if it is not that way, we can use some greasy. We can take for example, we can sort the colors by number of lamps of this color, then enumerate positions in a line in order, like all odd positions from left to right, and then all even positions from left to right. And it's not obvious, but it's not hard to see that if we will place the lamps in this order, then everything will be okay. No two adjacent lamps will be of the same color. The first and third colors are okay for sure, because the first will be only on odd positions and the third will be only on even positions. There can be some problem with the second, like we can fill some odd positions and then some even, and they will meet somewhere in the middle, but like odd positions on the right side, even positions on the left side, and they can meet in the middle, but it will not happen actually, because it means that there is like at least half of all the lamps should be of this middle color, which means that there is at least half number of lamps of the first, like the biggest color. So actually it should be half and half, and it's easy to see that in this case actually the first color will be on odd positions and the second color will be on even positions. So we should just check Obviously, it's if we want the answer to be no, then we want this number to be maximum. So we just check some inequality. The number of lamps of one color is more than 1 billion, but like there some will be up to 3 times like 3 billions, and that is too big for integer type, so we'll use long type. So we know the maximum, we know the sum, and to compare maximum and other two, like sum of other two, we should take sum minus maximum. So if m is strictly bigger than s minus n plus 1, then the answer is no. And otherwise it's yes. So the answer to this test is really yes. We can go 1 to 1 to 1 3 1, and that's good. So you really need that plus 1. So in problem B, we have array of numbers and some number s. We have to choose the largest possible prefix of this array. Then maybe okay, we have to choose some prefix, then maybe erase one number from this prefix, and then sum of all other numbers should be no more than s, and our score is a number of like not erased numbers on our prefix, and we want to maximize it. Well, if we fix the prefix, then like, if the sum of all numbers is no more than s, then we shouldn't erase anything because we want to maximize the number of not erased numbers, and otherwise we could erase only one number, and it's clear that we should erase the maximal number among the numbers we have. So we could just go from left to right, try all the prefixes, maintain sum and maximum element, and if the sum is not more than s, then we update the answer with just length of the prefix, and otherwise we check if erasing maximum will make everything better, like, make the sum not more than s, and if so, we will update the answer with length minus 1. We actually don't need the array. Let's not store it. We only have to maintain the sum and maximum element, and also answer. So if the sum is more than s, then we update the answer with s plus 1, which is length of the x. Otherwise, we want to check if sum minus maximum is no more than s, and in this case, update with length minus 1, which is just I. And that's all. Yeah, it's oh, we should print the ID. If there are multiple answers, print any of them. Okay. I don't want to store additional information. We can see that like this maximum is always the second part. Like they may be equal in this case, but like the longer prefix is always better if we delete one element. So we just have to maintain ID of maximum element. And like in this case we shouldn't erase anything, and in this case we should erase ID, and like this is always better than the last thing we tried. Oh, not the last, just all the previous things we tried. If it is possible, then it is not worse. Maybe not better, but not worse. And we can print any answer, so it's fine. So in this problem, problem C. We have a permutation of some numbers, and we also have a list of m different numbers from the same permutation, and we can we should do the following. We go through our list of lengths m, and for each number in this list, we will find it in our permutation, like in our permutation, which is actually stack. So it's stack in order from left to right. We will find it. We will take out all the numbers up to the number we want. Then we erase the number we want, and we have to put all the numbers, all the other numbers we take back to the stack, but we can do it in a different order, or maybe in the same if we want to. Every action, taking one number from the stack or putting one number back, takes 1 second. We want to go through our list in minimal time. Okay. It says that like when we doing something for this number, we should like take all the numbers up to the one we want, then erase it and put the numbers back. But let's not put the numbers back right now. Let's say that they're just waiting. When we will move to the next number, we will like put them back, but we want to do this like to just leave them wait, because we don't know the order we want the numbers now, but when we will go to the next number, like there are two situations. This number is either waiting or in a stack. If it is in a stack, it doesn't matter the order we will put the waiting, currently waiting numbers back to the stack, because we will take them back again. Like we put them in some order, then take them, and then take some more numbers up to the one we want. So the order is not important. And otherwise, it is, if it is waiting, then we could put like all the numbers but the one we want in some order, in any order we want, and then put the number we want on the top. If we do this, well, actually, we will just spend only 1 second. It is good. Like our number is on the top, which is good, and we don't have to actually put all the numbers back, because like we could place them in any order, and it actually means that they could still wait. We don't have to choose this order now. We will choose it afterwards. So in any moment of time, we have some numbers in stack, some numbers are waiting, and what do we have to do? We have to check if the number we want like is currently waiting. If it is, then like in reality, we would have to put all the numbers back to the stack in some order, like spending their number of seconds and then +1 to take the number we want from the top. But actually, we will just say that we spent 2 seconds to put the number we want to the stack and take it back, and all the other numbers are waiting. We will choose their order afterwards. And if it is not in the list of waiting numbers, then we have to put all the waiting numbers to the stacks and take them back, which is 2 times their size time, and then go through stack till we find the number we want. To implement this, we will store the stack in something, in just array, and store the waiting numbers in a set, so we can check if the number we want currently waiting or not. I guess we could just yeah, we don't need set, we could just use like Boolean array used. So if it is, we just erase it and do answer plus equal 2. Otherwise, we do answer plus equal 2 times number of currently waiting numbers, which we will maintain, and then go through the remaining of the stack till we find our number. Increase the answer each time. So it can seem it can be seen that it is squared, but actually it's linear complexity in total, because like the each operation we do in constant time plus the number of numbers we taken out from the stack and putting in the waiting list, and the total number of numbers in stack is linear, so total number of operations is actually linear. We don't need the array B. We will just we can do everything online. The answer is actually long, despite like the solution is linear and it kind of like do all the operations, but it the operations are done in some smart way. So I'm sure I can construct a test where the number of operations is like n squared divided by something. Maybe like after it's divided by something, it fits in integer type. But let's use long and don't think about it. So we want the number x now. If it is in waiting list, then we just do ans plus equal to 2. Oh, I also want the number of currently weighted numbers. Do this and k means month. Otherwise, we do ans plus equal to k, because we have to put all the k numbers back and then take them. And yeah, we also have to know current position in our array, which is step. So we are going through stack, and while we didn't find our number, we take it, put it in the waiting list, so the number of numbers in the waiting list is increased, the answer is also increased, and the position in stack also increased. And then we find our number, and that's all. It is not working. Oh yeah, in the end, like after I have done everything, there can be some numbers in waiting list, and I have to put them back. Now it is working. In problem D, we have some kits. Each kit has a list of presents he wants. Each list has some size and some different numbers representing the presents. Then we have some algorithm randomized, which does the following: choose one of n kits equiprobably, then it chooses some items that in the list of this kit, and then it also chooses different random kit, like maybe the same, just one more random kit, independent of the previous random choices. And like the situation is good if the second kit also wants chosen present, and otherwise it is bad. And we ask to find the probability that situation is good. And yes, it's pretty simple. Like after we fixed this item y, we just know we can calculate the probability that the second kit will be good for this present. It's just the number of kits that want this present divided by n, the number of all kits. Okay, and all of this choices we can just like brute force try all of them. Try one kit, then one present. The probability that we chose that kit and that present is just 1 divided by n times the number of presents in this kit list, and just add this to the answer. That's all. Pretty simple problem. Okay, I don't want vectors, I want the solution to be fast. To do this, we will do some smart things. First, I want to calculate the inverses of all numbers up to 1 million. To do it, there is a smart algorithm in linear time. It just works. It's not hard to show that it works when you know the algorithm, but to come up with it, I guess it's harder. So I want to calculate the number of kits for which want the given present. It's easy. Just read everything and do some increments. And then go through all the kits, all the presents, and calculate the answer. To do this, I have to go through input twice, and to do this, I have to store it somewhere. Probably I will need some vectors or something. I don't want this. I want to go through input once and not store anything. To do it, I have to I will calculate for each present how many kits wanted, and also I will for each present I will calculate the probability that it will be chosen as this present on the second step. How to do it? If the present is present, if the present is present in a list of some kit, then I this probability for this present should be increased by 1 divided by n, and n times the number of presents in this list. So let's just do this. So in array B, there will be a probability that present number I will be chosen on the second step. So this is this probabilities: 1 divided by k and 1 divided by nk. So it's 1 divided by k multiplied by 1 divided by n. So in array A, I could like count the number. Let's just add 1 divided by n. That's the probability that this kid will be fine for this present. And that's all. Wow, this is so lengthy statement. Okay, let's enroll it. We will probably have a permutation. Oh, no, we should. Find the cast lexicographic permutation, probably. So, okay, there will be something about permutations of length n. It says that element y is reachable from element x if we could start with x and like go to pair of x every time and then finally get to y. For permutation, it means that x and y lies on the same cycle. The permutation is a collection of cycles, and if we like start in some element and go using the permutation many times, we will go through on some cycle, and this permutation is just a product of these cycles. Okay, then we have some decomposition of permutation. It is as follows. We decomposition is a list of lists. At first, it's empty, and like all the numbers and permutations are not used. We go from left to right. if we find used element, we do nothing, and otherwise we find some unused element. We take the cycle in which it lies. For some reason, in order they appear. Okay, then we yeah, we take the numbers in order they appear in permutation. Then cyclically shift this list so that maximum is at first position, and add this list to the our list of lists, which is a decomposition, and mark all the elements as used. Okay. Okay, then we sort the decomposition by the first element in this list. It's the same as sort lexicographically, and then concatenate all the lists in one. Okay, the permutation is called good if this transformation produces the same permutation. And we are given n and k, and we want to construct the case lexicographically good permutation. Okay, so I'll be right back. I will think about the problem for a bit. Okay, I'm back. This problem looks hard, much harder than the previous ones, but I think like we should start unraveling, and maybe it's not so daunting, really. Let's start. Can I just create empty one? Thanks. Okay, so we have permutation. We don't have it yet, but let's try to understand something about these good permutations, which are equal to the transformation. Okay, it should be equal to the transformation. How does the transformation look? Well, it has some groups which were cycles in some order, and these things are equal. Okay, let's say here's some number. So the same number should be here, and we know this is the maximum number in this group because we cyclically shifted it. So this should be like the maximum on this prefix. This element lies in some cycle in our permutation. And this cycle is actually this group. Each group is all the numbers lying on some cycle. So this number lies in some cycle. We have some cycle. And this cycle should be this group. It is easy to see that numbers which are lying on our cycle, like the set of these numbers actually is the same as the set of position of these numbers, position of our cycle, positions of our cycle, because this number is the position of the next one, and they're in cycle, so all positions of next one is the same of all positions of all numbers, and all positions of the next numbers is just the set of our numbers. So the set of our numbers is the same as the set of positions. Okay, but we know the set of positions. Like this is the set of positions. So it's the set of positions is some prefix, so it's 1, 2, 3 up to something. Like if there is 4, then it's 1, 2, 3, 4. It's up to some key. Also, this thing is maximum, so it's actually going here, and then like we should construct some cycle which should end here. Cool. After we have done this, we can just like we have used all the positions from 1 to k, and we used all the numbers from 1 to k. We could just cut it, and like the next the suffix of our permutation constructed like the same way. We should construct the next block. There will be some number. It will go here to the start cycle. So there will be the end of this cycle. And it's like the numbers k plus 1, k plus 2, and something. So our permutation is like we should divide all the numbers from 1 to n in groups of consecutive numbers. So this will be the size. The sizes of these groups should be the sizes of these groups. Then we will somehow permute these numbers in such a way that it will be one cycle, and the first number is maximum. So we will construct this and then go to the next thing. Okay. We have kind of understand how does this good permutations look like. How do we construct lexicographical case one? Well, usually in this such kind of problems, like construct case object, like lexicographically means that we like, let's say we want to construct minimal one. We should minimize the first number, then the second, then the third, and so on. How to construct case? Okay, we will try to set one here and see how many ways there are to continue. If there are enough ways, like we want to construct case, and if the number of ways is at least k, then okay, we should start from 1. Because if we will start from something bigger, we will get, like, let's say there is W number of ways, we will get something like W. The first W permutations starting with 1, then they will start from something bigger. So if k is less than, like, less or equal than W, then we should start with 1. Otherwise, like, we shouldn't start with 1, we should start with something greater. And we could say that, like, forget about starting with 1, it will not do any good. But there were, like, the first W permutations were starting from 1, and we should say, okay, let's decrease our k by this W, and start from something bigger. Okay, so like, to do this, we should somehow understand how to calculate the number of good permutations with some fixed prefix. I don't know how to do this now, but I think we can do something else, a bit different. Obviously, we are starting from like choosing the first number. Okay, but if we have chosen the first number, something here, then we know that first S numbers should be in first group, first cycle. Like, this is our first cycle, and then something else. Here we should use all the numbers up to S minus 1, and then we will use S plus 1, S plus 2, and so on up to N in the ending part. Okay. Let's say we know how to calculate the number of overall good permutations of length n without some fixed prefix. And I will explain shortly how to do this. Okay. This is the part of explanation, actually. Let's say we know how to do this. Okay, but then, like, we should choose somehow how to use these numbers from 1 to S minus 1 here to construct a cycle. Let's say we have choose a way that is that has index k1 in a lexicographical order of all the these things, permutations of length S, which is one cycle starting from S. And then, like, when we construct this, we want to construct some permutations on all these numbers, and let's say it has index k2. Again, index k2 among all the permutations of numbers from s plus 1 to n, which is actually the same thing as like just all the good permutations of length n minus s, just add s to all the numbers here. So what will be the index of this thing we have constructed among all the permutations of length of all the good permutations of length n that are starting with s? I say that it is actually k1 times n minus s plus k2, where this p is the number of good permutations of size n minus s. Why is that? Let's look how is the least lexicographical order of this permutation works. We want to choose minimal thing here, then minimal thing here. How do the next one looks? Like second one here, and this is still the minimal. Then third, like, to compare two permutations of some of this kind, we should at first compare like left part and then compare right part. So third order looks like this. First of this and append with all the this number of okay, if it is one indexation should be k-1. Append with all the possible permutations here. Then take the second one here and again append in with all the permutations of size, good permutations of size n minus s in lexicographical order. Then take the third one and so on. So okay, let's leave in zero indexation because it's easier as it. So in zero indexation, this is the number. And it works the other way around. If we know what is the index, the permutation we want to construct, this thing, how to know k1 and k2? That's easy. This is our k actually. Then k1 is k divided by this p. Rounded down, and k2 is k modulo this p. So if we know how to calculate this and how to construct this thing with ADK1 and this thing with ADK2, then we are done. Let's first talk about how to calculate this thing. Well, actually, to do it, like it's fairly easy. We just calculate dynamic programming. Like this thing will be the state of our dynamic programming. We will try all the values of s. Now, like with given s, we have to add like the number of how many these cycles exist and how many ways to append permutation of size n minus s. This is just p n minus s existing. So p of n is the sum over all s. Like how many ways to construct this times how many ways to construct this. This is just Pn minus s. P0 is 1. And this thing, like how many ways to construct the cycle, is actually fairly easy. From S we go here, then from here we should go like any place we haven't been, but also not there, because if we go there, then it will be not one cycle but many cycles. So from here we go to the end, then we go somewhere, then we go somewhere. Like we should visit all the places, and only then, only when we visited everything, like this, only from this we can go to the first place. So the number of ways to choose for this guy is s minus 2. Then the number of free positions is decreased by 1, then also decreased by 1, and so on, up to 1. And then we also don't have choice, we go to the first position. So this is actually just s minus 2 factorial, and okay, we have to assume that minus 1 factorial is 1. Because just 1 is also a valid way to start. So this is fairly simple dynamic programming. So we can calculate P. Okay, now we have to find a way to construct case of these cycles and case of these things to append. The second part is actually just recursive. Like we should solve the same problem just on smaller permutation. Like we now want to construct this case permutation of good permutation of size n minus s. That's just a recursive call. So the only thing left is to somehow construct lexicographically case cycle of length s starting with s. And I did not find a way to do this yet, but I think it can be done. Maybe now we should use the knowledge, like build it from left to right and somehow compute how many ways there are to continue. It should just be one big cycle. I think, like, yeah, it's not that hard. Like if we have, like we want to construct a permutation of size s, we know some prefix. We want to calculate how many ways there are to continue. Let's draw oriented edges from position to the position we want. If there are some cycles, then if we are at the end and we just want to check if it is one cycle, it's easy, just check. And if we are not at the end and we have some cycles, then there are no ways. We already fucked up. And otherwise, we will have some chains. Yeah, we could have something like this, like two edges go into one place, it just means that it's not permutation. Like if we have this and this, it means that on these two positions they're equal numbers. There are also no ways. And otherwise, we have some chains. There are also chains of length 1, maybe. And we just have to connect all of these chains in one big cycle. If we have m chains, then there are m minus 1 factorial ways, I think. Yeah, we just like take the first chain, which starts here, and choose some order of chains that will be in cycle. So if we have m chains, then this number of ways to continue. And actually, like this number don't depend on anything. Like it just depends on how many, how the length of this prefix, how much edges did we draw. Like we know that if we didn't draw anything, then there are s chains. Then if we draw some l edges, then we will have s minus l chains. So we should just check if everything is fine. Like there are no cycles and there are no situations like this when two numbers are equal. So okay. This dynamic programming we should calculate only once. So it's just n squared and nothing else. But this thing is not so fast. But for one test, we will find this s in linear time, and then we will do a call to a function like build the case, the cycle of length s, and this total lengths we will use sum up to n. Like we will build one cycle, then second cycle, third cycle, and sum of their lengths is n. So if we will build this cycle like in some cubic of s time, it will be fine. And we actually do it in like we do linear search here. We do linear search for each number, and for each thing we should do some checks, like there are no cycles and no situations. It's also linear, so this is s cube, and like the total complexity will be actually n cube, which is fine. So yeah, we can write this. And let's hope the problem f is not that hard, because otherwise we won't have enough time. There are also some problems with infinities. Like if we don't do anything, we will just overflow long, because it looks like the number of good permutations is pretty big. So we should write some functions which will return the minimum of result of operation and infinity. and we should be careful. Like I couldn't write the same thing, just return minimum of inf and x times y, because x times y is can be overflow. That cannot, and that can be overflow. So we will check this. This should be fine. So I want to calculate this dp. Well, let's call it p to maintain the same notation I used. So I don't want to take -1 factorial. I want to do this if s equal to 1. I can just add p n minus 1 here, and let's go to zero indexation. If k is bigger than the number of good permutations, which we should just print -1. Otherwise, we call solve and print it. So now I want to try all the s values. Yes, I will use zero indexation, so I used one indexation for s here, but let's use zero indexation. So I'm going through the first element, and now I want to calculate like this number and compare it with k. This number it's just this value for fixed s, like how many good permutations with the first element equal to s. No, not just times, but not, because we are false. Okay. So if there are less good permutations starting with S than K, then we decrease K by W and try next S. Otherwise, this S is good, and look, we now want to construct a cycle and append the suffix. So and we also have to know how many, like, what are the K1 and K2. But they're just written here. So this is the cycle of S. And this should be K divided by n minus S minus 1. And this will be solved recursive. So I concatenate the cycle and good permutations of size n minus S, and I should increase those values by S. So what is left is to write the function get cycle. I'm trying the next value. It shouldn't been used before. And also it shouldn't create a new cycle. If it does, then it means that this is bad, but we should just check if this element don't create new cycle. Well, we just start from it and go till we get to nothing, or get to this value, which means we get a cycle. So it's not a cycle, then it's valid way to continue. And there this way this number of ways to continue. If it is smaller than k, then we should decrease k and continue. Otherwise, we should say that it is good and will break. I doubt this will work. Oh yeah, if n is 0, then we shouldn't do anything. There are some mistakes. Okay, so the first one, this probably says that this function doesn't work properly. It did return 1 minus 1, I guess, which is bad. Oh yeah, like if yes, if we are at the end, that just means that the only element is good, so we just say this. Now looks like it works. Some string problem. In half an hour? I don't think so. Yay! Okay, so this is not a string problem. But now I don't understand why it's not obvious problem. Okay, so we have some string of zeros and ones actually. Like we can do anything but change the case of a letter. So we just say that lowercase letters are zeros and uppercase are ones. So we can choose any segment of a length L, where L is given, and either set all the elements to 0 or to 1, and we want minimum value of minimum of lower and like minimum minimum of number of zeros and number of ones to be as small as possible. Minimum. Okay, then it seems that we can just either do a number of zeros to minimum or number of ones to minimum, the one we want. So we will just try both. So now the problem is the following. We have a sequence of zeros and ones. We can take a segment of length L and either set it to 0 or to 1, and we want to minimize the number of ones. Well, the first observation, we don't want to make ones, so we want just to set zeros. So we actually want to take some number of segments, set them to 0, and minimize the number of ones. And then do like inverse everything, like 0 to 1s and 1s to 0s, and do the same thing again. Okay. Why it's not easy? Yeah, I guess because we have some freedom of what segments to set 0. We can restate the problem as follows. Oh yeah, there is also a bound of how many times we can do the change. Okay, so after we do this key changes, there are some ones, and we could say that we are paying one coin to make this one 0, and we want to get all zeros. Then we could go with some DP, I think. Let's look at the leftmost one. We could either pay one coin and like just make it 1, or we could pay one segment and take any segment that contains this one, but it is the leftmost one, so it's kind of obvious that we want the segment as much on the right as possible. So just starting from this point, or if it goes out of the string, not just some suffix of our string. But that's still slow. Maybe we should use some DP optimization here, but it's not clear. Okay, I don't know how to solve this. We have 20 minutes. Let's try some lambda optimization. Maybe it will work. I don't think so. So, DP optimization. I want to say that like we can pay one coin for just changing one to 0, or we could pay like we are paying 0 coins to change some segment to zeros, but we can do it no more than k times. But let's say that we can do it infinitely many times, but we are paying something. What do we pay? We are paying some fixed amount called the lambda, and on this we will do linear DP to make everything into 0 in minimal cost. And then we will find such lambda that the optimal solution uses, well, one of the optimal solutions uses this k segments. And let's hope that this will work. Oh yeah, and we will find it using binary search because reasons. Like if the function, some function is convex, then it will work, and I don't know if it is convex or not. If like the total length of segments we can use is at least n, then we can cover everything. I'm just ifing this so I won't have corner cases in my DP, I hope. So binary search. Let's go. Okay, so if we are paying 0, then we won't use any segments. The cost will be 0 because we will cover everything with segments. Okay. And if the cost is infinity, which is actually n, then we will not use anything because we could just pay the number of ones and not use any segments because they're too too costly for us, too expensive. So now we are doing binary search. solve. Okay, solve will return the cost and what is the minimal number of segments such that the minimal number. So, what is the minimal number of segments? So if the cost is if lambda is 0, then we use many segments. If it's infinity, we use 0 segments. Okay, let's say okay. If this if the minimal number is smaller than m, we will say that it is in right border, and otherwise it's in the left one. So in left border, it's in left border it's strictly more like now we want to use infinity segments, and the cost will be negative. And in right border we use not more than m segments. So the real answer will be ans first minus ans second multiplied by m. Hopefully. Okay. So yeah, I think I should say this. So if the cost of one segment is 0, then we will use 0, obviously. But I want the minimal number of segments. Come on. Why is this so hard? Okay, let's calculate dp first. I guess dp should be also this. Okay, I could just say this. So I want to use a segment of length L, but if it is if it goes on the right, we just take minimum. So to do this, my new value will be what? I'm using one more segment, and this is plus lambda, because I'm using one more segment. And also I could just go one step further, and if it is 1, I should pay 1. Okay, this should be okay. -1. Cool. -1. Maybe it's just not working. Oh, why I'm multiplying this by m? This is like this is the DP value. I used exactly m segments. I didn't use exactly m. I used this number, but m is also okay, probably. And each segment costs r, but should cost 0. So cool. I will be surprised if it is accepted. Cool. Okay, let's go once more time through all the crazy things I have done. So main is simple. That's what I said in the beginning. And just convert the input to zeros and ones. Try to solve, and then try to solve in the other direction and take a minute. So function solve tries like it has an array of zeros and ones, and it tries to solve the problem. Like we want to turn all the arrays, all the array to zeros. We can at most n times take a segment of length L and just set zeros, and this is for free. And also we can pay one coin and turn one to zero, and we want to spend minimal number of coins. Then we say that this bound on that we can use at most m segments. We don't like it because it slows our solution. We could solve this in quadratic time, n times m time, with dynamic programming, because we have to maintain in DP state how much segments did we use. And we don't want that. So we want to just say, okay, let's use as many segments as we want. But this changes the problem. Now we just can cover everything and cool. And like do everything 0 coins. So now we want to transform problem a bit and say that now using the segment is also not free. We are paying something, some value called lambda. And this new problem can be solved with dynamic programming in linear time, because now we don't care how many segments we used. We just let's look at prefix and what minimal amount of money we should spend to turn it all to zeros. And we have transitions, like from any place we could take a segment and pay lambda, or we could just go to the next element, and if it is 1, then we should pay, turn it to 0 in 1 coin. Otherwise we should do nothing and just go to the next prefix. I'm doing this here. So this new problem can be solved in linear time. How does that help? Well, if some function like cost of lambda is convex, then like for some crazy reason well, there is a thing called lambda optimization, this thing I done here, which says that like for each value of m there will be some lambda such that we can use exactly m segments and it will be optimal for this lambda. But if we fix m, then lambda is irrelevant. Like if we use all the segments, we just pay m times lambda and forget about it. Just pay it, and like the rest of the solution is the same as we didn't pay anything. So the real cost will be like the cost in RGB minus our lambda times number of segments we use. And like if this function is convex, then correct lambda for a given m can be found with like this binary search. And that is what I'm doing. And maybe it is correct solution for this problem. I don't know. Like, to prove the correctness, we should prove that the function is convex, and this is usually hard to do. And like in some cases, it can be done using the fact that there are some slower ways to solve the problem. For example, many times it have been done like saying that this is an instance of min cost max flow problem, and the solutions are convex. We know that, so we can use DP and use lambda optimization in this DP. And in this case, I don't know. Maybe it can be done somehow. So let's take constant strings. Oh, okay, not bad. Okay, thanks for watching.